Hello everyone, welcome to the Maple Workshop for 2023. I'm Ronald and I'll be presenting the first half of the seminar. Right, let's get started. So let's get to some basics. So Maple, like any other math thing, would use a plus for addition, a minus for subtraction, a asterisk for multiplication, a slash for division, and a caret for powers. So, obviously, something like 1 plus 1 is going to be equal to 2. Yeah, so just to note, this workshop is aimed so that everyone who's watching does follow along. So, I'm going to be at a pace where you can just type in whatever I'm doing, or if you want, you can just type in something else. Just try out whatever you want to do, just to, experiment with the program, see what you can achieve with it. So, obviously, we also know things like 1 minus 1, that's 0, to the power of 3, that's 8. You can also divide things. Pretty cool. So, Maple also has parentheses, which are just these brackets, and they're used in the same way that you might use normal expressions. So, generally, you're using it to group expressions. So if we try out the first example, which is minus 1 to the power of 1 divided by 2, that's what we get, minus 1 half. And the reason is because this 1 to the power of 1 is grouped up, which becomes a 1. You divide it by 2, so you get a half. And then you have the minus in front. So you get a minus 1 and 2. But if we put brackets around the half, then instead it becomes 1 to the power of a half. So that becomes a 1 in total, and then the minus makes it a minus 1. We can also put brackets around the minus 1, make it to the power of a half, and then this makes it I, because the square root of negative 1 is I. Now, we also have variables in Maple. So the way we use variables is we give it a name, maybe f1, like in the example. We use a colon equals, and that assigns it to something. So the thing can be anything. For example, most likely a number, like 6. And what that means is whenever you call f1, it gets replaced with 6. So if we do something like f1 times f1, we get f1 squared, which is 6 squared, 36. We can also give it expressions. So we can give it something like expx. So just remember that when we're assigning variables, we use colon and then an equals. So expx means the exponential function. So it means e to the power of x. And the reason we don't use e to the x like this is because you might see that e is kind of in italics here, but it's in normal print here. And the reason is because e is actually a variable name in Maple, which means that it's not reserved to Euler's number. It's just a name. So we could, for example, do e and then assign it to 1. Then e to the x would just be 1 to the x, which would be 1. And something you might notice is that variable names, they have to first start with a letter, but then it can be followed by numbers and letters. And then we also have things like it's case sensitive. So if we create a capital F and then a 1, and then we use colon equals, assign it to a 2, we see that F1 with lowercase is 6, but F1 with uppercase is 2. Now, there are also some reserved names. So, for example, D, if we let this be equal to a number, we can't do it because D is a reserved name and it's used for another command. There are also some ways to unassign variables. So we've made all of these variables and given them values, but if we don't want to use them anymore, we could either individually remove them, or you can just reset them. I personally reset them all the time, since once you're done with the question and you move on, you don't really need the previous variables anymore, right? But to unassign a single variable, you do F1, and then you colon equals, then you put quotes, then you put in the name again. And then what that gets you is F1 is equal to F1. And then if you type in F1 again, you no longer have the value of 6. Or you can do restart. And what that does is it gets rid of every single variable. So you'll see that F1 was originally 2, we restarted, and now F1 is F1. And Maple also has constants. So the main ones in Maple are pi, I, and infinity. So something else you might find useful is something called eval_f. So if we do eval_f and then maybe do something like 2 times a variable such as pi, we will, this wrote eval. It's eval_f. Yep. Eval_f takes a number and then displays it to 10 significant figures. And that might be useful if you're trying to get an approximation, or the question literally asks, hey, can we get this in 10 significant figures? And something else that's really useful is this and sign. This percentage sign. And the reason is because what it does is it repeats whatever's in here as a variable. So you can do percentage to the power of percentage. We get this number squared. You can do all sorts of operations, right? But then that also means that you're able to make use of the actual variable here inside other commands, because, maybe it's cumbersome to type all of this out again. So that's pretty much the basics. We'll move on to types of functions. So there are 2 types in Maple, an expression or a function. So an expression is given by E. An example of an expression is given by E. We can assign it with colon equals, and then maybe, let's say we give it x squared minus x. So we have E equal to x squared minus x. And then a function is a bit different. So you give it the name, you give it the colon equals, then what you do is you write the variable, then you put an arrow, now you write the function. So there's an easy way to tell if something's a function or an expression in Maple. In this blue text, if there's no arrow, then it's an expression. If there is an arrow, then it's a function. The main difference between a variable and a function is how you differentiate things and how you would sub values in. So we'll go through differentiation later, but for what you need to know now is that for functions, if you just say function and then bracket whatever x value you want to put in another bracket, that gets you 4 of f. Sorry, f at 4. Yep. And then to use it in an expression, you would need subs, then x equals 4, then the expression. And what this says is we want to substitute x with 4 in the expression e. And the reason we do that is because if we try it with e, we'll get this because it's not an inbuilt functionality, since they're not expecting you to be able to put in numbers as if it was a function. So instead, we have to use this subs command. And we can also make functions with more than one variable. And the way we do that is we have x, for example, this example, which is, we'll give a name of d. We put the multiple variables in brackets. So we have x, y, and z in here. And then we have an arrow again, because it's a function. And then we can just type in whatever we want. So here we can have square root of x squared plus y squared plus z squared. Now, what we can do is we can actually just use it like a function. So if we wanted to sub in a point, for example, 1, 2, and 3 as a 3D point, we can just put it in and we can evaluate it. And we can test that's true because 1 squared is 1, 2 squared is 4, 3 squared is 9. So when you add it all together, we get 14. Alright. Maple also has some inbuilt functions. So one of the ones is the absolute value signs. So for example, in the example we see the absolute value of x minus 2. And the way we do that is abs as a command. We can also take square roots with sqrt, and then let's put in a number like 10, and it gives us the square root of 10. Now, what we can do is we can do sine pi on 3. So, sine, tan, cos, things like that, the trig is available here. And of course, we use our pi variable, pi. So we get pi on 3, and then the sine is root 3 on 2. We can also do arcsine, and the way we do that is arc, sine, and then let's just take in what we had before with the percentage sign. So arcsine is just the equivalent of the inverse of sine. So arctan is the inverse of tan, arccos is the inverse of cos, and so on. And we'll see that this percentage sign is, percentage sign is going to take in this value right here. So it's arcsine of root 3 on 2. So if you evaluate it, you get pi on 3. Now, Maple also has packages, so not all functions are available to you immediately, but you can get access to these functions with the with command. So with, no capitals here, and then you have to write in the name of the package very clearly. It's going to be something like capital L, linear, capital A, algebra. So no spaces. And if we press enter, it gives us a list of every single function that we can use. But we can also mute this if we use a colon. So the colon just removes the output for this one, and it just makes it much cleaner, right? Because without the colon, you'd be seeing all of this, and it can get a bit messy. It displaces everything up here. So we'll actually only be using 2 packages for Maple this term, which is going to be plots and then linear algebra. So we will run to restart, and the reason is because we've already assigned an f. So if we assign f again, it's just going to give us an error. Let's just give a quick example. So if we have f equals 1, actually no, it should be fine. But yeah, it's just something that I wouldn't mess with. If there's something that could happen if you use the same function name repeatedly, so it's just something that I'd avoid altogether. But yeah, we can also create piecewise functions. So for example, we can get f to be equal to the piecewise, so we use the piecewise keyword to get a piecewise function. Then it's condition first expression next, right? So we put in the first condition, which is x being less than 0, comma, then the expression, which is 0, comma, next condition, which is x being less than 1, comma, and then x squared. Now we do another comma. We can do the last expression, x greater than 1, and then comma, the last condition, and then the last expression, x. Remember the multiplication sign between the 2 and the x, and then minus 1. And we get the piecewise. And I ask you to do that because if you see, it's going to say that it's a missing operator since it can't tell that 2 and x is a 2 times x. So we have to specify that it's 2 times x. And something else you can also do is you can remove the last condition and then it replaces it with an otherwise. So to substitute in a value, we might think, oh, it's an expression, right? And the reason is because there's no arrow here. So we use subs. X is equal to minus 1. And then we give it the expression, right? That's what we learned so far. But we see that it doesn't actually work here. Because what happens is, subs substitutes in the values, right? It replaces every x with a minus 1. That's its job. But it doesn't actually evaluate it. So if you want to evaluate it, you would have to put eval in front of it, like so. So it's saying after you substitute, we evaluate it. And you'll see this is correct because minus 1 is less than 0, so we get 0. Now, we also have some functions for factoring or expanding in Maple. So the way we can factor is we could, for example, give it a polynomial. Then what we might see is that we use the factor command and that would get us the actual factors. So we can also use the expand command to expand out polynomials, which might be factorized like this. Or we can use it to expand cos A plus B. So trigonometric stuff as well. But something might happen, for example, if A is equal to pi, and we try this expand again, you might see that it becomes minus cos B because it treated this A as a pi. So cos B plus pi is just minus cos B. So it's a key tip. If you are using a variable and you have it previously assigned, you should try to remove that assignment. Then it should work out. So just A assigned to A, and now if we try this again, it should be fine again. So we can also simplify. So if we write simplify, we can put in something like ln of x squared plus 2 to the power of 5 divided by 2. And what that does is it takes this number right here. So we have 2 to the 5, which is 32, divided by 2, which is 16. And we also have normal. And what that does is it takes some rational functions and then just combines it. So this is something that you might have seen in partial fractions. It takes two fractions and then merges it into the original whole fraction. So that's pretty much everything about the actual functions. We'll start going through calculus. So we can evaluate limits, and the way we can do that is by using the limit keyword. Then we type in the expression we want, for example, sine of x over x. Now, comma, we give it the actual variable we want to assign it to. So we have x equals 0, which means we want the limit of sine x on x as x equals 0. Now, we can also do this with other numbers as well. And we can also do it with infinity, which is one of the more useful parts of it. So the limit as x approaches 0 for sine x on x is 0. Now we can also take left-hand side limits and right-hand side limits. So the limit as the absolute values of x minus 2 over x minus 2. Now we want x to be equal to 2 in our limit because we're approaching x equals 2. And then we give it a left or a right. So if we give it a right, it's going to give us the right-hand limit. And we give the left, we give the left-hand limit. And something you might see is if we don't specify, it's going to be undefined because the left-hand limit and the right-hand limit are not the same. So we can also take derivatives, and the way we take derivatives is by using a diff command for expressions. So if we have something like y colon equals the e to the x multiplied by sine x squared, and we diff it, we write the expression we want, y, and then the variable we want, x. And we get it. Now, if it's a function, x is an input, and then the output is e to the x multiplied by sine x squared. We get this function. We know it's a function because there's an arrow here, and then we diff it by using d and then f. So what we might notice is that there's no arrow here, so diff takes in an expression and gives out an expression. D takes in a function and gives out a function. And the reason why it's useful that it's a function is because we can also substitute in points as if it was a function, like so. But if you wanted to substitute something here, you would have to use subs. We want x to be equal to 2, for example, comma, the expression, and then another bracket, and then you can substitute it in. So we can also take higher derivatives, and the way we do that is we can take, say, diff sine 5 times x, for example, and what we can do is we can just add more x's. So adding 4 x's means the 4th derivative. Adding 5 x's is the 5th derivative, and so on. So this right here is the 9th derivative. And you might see that it's getting a bit tiring to do very high derivatives. So we can just replace it with diff sine 5 times x, comma, and then x $9. And what this means is we repeat x 9 times. So we repeat whatever's before the $, after the $, times. So we see that these two are the same. Since there are 9 x's here, we also have 9 x's here, so we get the same derivative. Now we can also do implicit diffs. So the way we do that is first by finding the keyword, which is implicit diff. Now we put in the expression we want. For example, x squared plus y squared equals 1, which is the unit circle. Now you define what variables you want to be diffed with, such as x and y. Expected. Maybe we define something for it. still 1. Has to be the type. I see, okay. So the reason why we had this error was because we have y here, but y has been defined up here. So this is what I was talking about. If y is defined, then it's not going to be able to differentiate it. So it's always a good thing to restart between questions. So if we try this again, we should get the diff of y with respect to x. And if we swap the order, we get the diff of x with respect to y. So that's the difference. That's why we have y in front of the x. Now, if we want to substitute in a value, we can do subs. Maybe we want x equals to a half, and then y equals to square root 3 onto then d, which is the expression we want. If we substitute it in, we get minus root 3. All right, so now we can also implicit diff some other things. So, for example, if we were to take this function in here, we have x to the 3 plus y to the 3 plus 1. And that's equal to x times y plus 1 to the 3. We'll see that it won't work because we need to put in our arguments. So the arguments just say diff y with respect to x. So diff whatever's first with respect to whatever's next. So we can also minimize and maximize expressions, and the way we do that is we use the minimize function. So we have the minimize keyword, then we write in an expression such as sine x plus cos x, and then x equals to minus pi dot dot. So what dot dot means is every number between minus pi and pi. Every number between this number before the 2 dots and every number until every number after. So what this does is it minimizes between minus pi and pi. So you can think of this like a range or a closed interval. So now we have minus root 2 as our minimum. Now if we maximize, we can also see that we can put in a expression by itself, and what that will do is it will globally maximize. So it means it will find the global maximum value. Oh, okay. So I think so the issue here is that we have to use maximize and minimize with a Z because it is American spelling. So if we use an S, it's going to be wrong. And since it's not the exact keyword, it's not going to work out. And that's the maximum. So we can also integrate. And we can integrate using the int command. And the way we do that is we first define an expression, x squared times sine x. We know it's an expression because there's no arrow here. And then we can, to do a indefinite integral, we just write int, then we put in the function that we want, and then we have x. So that integrates it for us. You'll see that there's no plus c, and this is a expression. Now, if you wanted to, for example, integrate between a range, you can let x equal to a range. So the lower bound, such as 0, and then you do dot dot, and then the upper bound, such as pi. And that'll give you the integral. So now we move on to collections of expressions. I'll just take a quick sip of water. Sorry about that. We now have expressions. So we have sequences, and in Maple, a sequence is a list of things separated by commas. So, oops, that's not a comma. That's a list. Sorry, that's a sequence. Then we can also make a sequence with the dollar sign that we might have seen before. So 3 $4, it means repeat 3 4 times, which is what we see here. Or we can use the sequence command. So sequence, which makes a sequence, and then we write in an expression. Maybe something like k squared. And k, we can give it a range, such as 1 to 5. And what that does is it starts at 1, puts it into the function, makes it the first element. Then goes to 2, puts it in the function, makes it the second element, and so on until we get to 5. We put it in here and then makes the last element. So we can make this range whatever we want, as long as it's in whole numbers, I'm pretty sure. So this might not work because 7 is greater than 5. So there's no number between, which is greater than 7 but less than 5. So maybe we do 10. And that gives us the squares between 7 and 10. And of course, we can also edit this. It could be k squared plus k plus 6, which also works out. So the difference between a list and a sequence in Maple is that a list has square brackets. See? No square brackets, sequence. Square brackets, list. Then we also have sets. So if we do a set, we put curly brackets around it. Curly brackets, set. Square brackets, list. No brackets, sequence. So the reason you might have only seen 1, 3 here, even though there were 4 originally, was because it's a set, which means any repeated elements are removed. So if we add another 3 in here, for example, $5, it's not going to change anything because 3 is already a variable in there, so it's not going to add any more. And the reason we use lists is because, for example, if we define a list, s1 colon equals, so it's just like any other variable. If you want to define a list, you set it to a variable, colon equals, and then you maybe let's give it 3, 8, 0. So what we can do is if we want to access a certain variable, we can do S1, and then in square brackets, we let it know we want 1, which means we want the first variable. So in Maple, it's going to be 1 indexed and not 0 indexed. And what 1 indexed means is that the first element gets the number 1, the second element gets the number 2, and the third element gets the number 3. And something you might see is that if we have a 2 to 3, this means give us all of the elements between 2 and 3. So we got element 2 and element 3, and we got a list. Now, we also have reassignments. So the other thing about getting a specific item is that we can colon equals, and that reassigns it to, for example, 12. So we see that the 8 became a 12 in S1. So now let's move on to sums and products. So for sums and products, we have a list such as S1 over here. And what we can do is we can use the add keyword. Then what we can do is we can give it an expression such as k squared. And then we can do k being equal to our list. If we do this, what we're actually doing is we're taking the first element, making it squared, and then adding it. We're getting the second element, squaring it and adding it. We're getting the third element, squaring it and adding it to get this total. And we can confirm this is true by squaring this, adding 12 squared plus 0 squared, and that gets us the same answer. So, this is not the only thing you can do with it. If you want to, for example, just sum the actual numbers in a list, we just let it be equal to k, because this means 3 plus 12 plus 15, 2 plus 12 was 0, because we're not changing the actual variable, we're just keeping it as is and then adding it together. Now, we can also do some other things. We can add a 2, we can put this to the power of k, etc. It'll all work out. So, we can also do multiplications. So if we do, for example, k and then mul, we would get 0. And the reason is because 3 times 12 times 0 is 0. And we can multiply the squares plus 1, and that would get us 3 plus 1 times 12 plus 1 times 0 plus 1. So if we try that out, we get 3 squared plus 1. And then we multiply this with 12 squared plus 1. And then we multiply it with 0 squared plus 1. Oops. 0 squared plus 1. And that gets us what we have right here. So we can also do sums with the word sum, but the reason we don't do sums with the word sum is because it doesn't take in a list. It only takes in a range right here. So the way we do that is we give it a range, we get 55 because that's the sum of all numbers between 1 and 10. And what you can also do, which is cool, is you can add to infinity in this. So if we have something like, instead of a geometric series like this, which we know converges, if we add to infinity, we get 1. But the other thing is, we can instead also define it to be a variable. So if we give it a range and a variable, it'll give us essentially a formula which we can plug in to get the number. So now that we know that, this is the same way that it works for product. And then we have manipulating structures. So what we can do is we can use NOPS, N-O-P-S. And what that does is if we put it in a list, it'll get us how many elements are in that list. So there are 1, 2, 3 elements, so we get a 3. Now we can also use op, and what op does is if we put op in, it makes it into a sequence. So remember, square brackets list, no brackets sequence. Now what we can do is we can also add square brackets, and if we do op S1, then we add in a different sequence, it actually combines it. So the reason we might use op is to either combine it into combine two lists, or take a list and put it into a different list. So what we can see is that we can actually replace this with op S1 as well, and that would give us a combination of two lists. Now, what we can do is we can maybe give L, which is a list, some variables such as x, or x squared, or x to the 3. So we see that we can have expressions in here as well. So in the same way, we can use the word subs, give x a value like pi, and then we give the list L, and what that does is it takes this and puts pi in place of every x, so we get x, which is pi, x squared, which is pi squared, and x cubed, which is pi cubed. So now we can see that we can also do other variables, like 1, or 0, or 2, things like that, not too bad. So we can also use a map function, and the reason why we might use map is because what map does is it takes a function and applies it to every element in a list. So in our list we had a 3, a 12, and a 0. So it caused 3, it caused 12, and it caused 0, which got us 1. Yep, and that's pretty much it for my section. We'll be moving on to complex numbers and equations, and that will be taken over by Fred.
Moving on is we're going to be looking at some complex numbers and equations. So as you know, we represent that as the square root of -1, and as with any real numbers, we can also add, multiply, and do all of those normal operations with complex numbers. Okay. And there are two different functions that we do use. Eval-C, we use that to evaluate exact Cartesian form, and eval-F is for a numerical operation. Okay, so let's assign Z1 to equal 2 plus 3 times I. And if we copy out this function, eval-F, Z1. As you can see, we sort of get like a numerical approximation, 63.0, but that is, of course, still an exact number. If we gave it a different number, that would make it, say, for example, like an irrational number, it would give out a numerical approximation. And if we instead did eval-C of Z1, we get the exact complex number 2 plus 3i. Okay. And a lot of your basic complex number operations, such as real, imaginary, argument, modulus, and conjugate, these are all built in within Maple. So again, if we want the imaginary part of Z1, we just simply call im of Z1, and that would extract out the imaginary component. Okay, and same with the real component. That's just going to be re of Z1. For the others, we have the argument function that just simply calculates the argument of our complex number. That's going to be the inverse tan of 3 on 2. And if you want to evaluate that to an approximation, again, we can use our eval-F command and put in our previous answer percentage, and that would get out numerical approximation. Okay. For the modulus of a complex number, we simply just use the absolute value function. That also works for complex numbers. So absolute value of pi plus I, that's going to be the square root of pi squared plus 1. Okay. And the last one is just the conjugate function. That just simply returns the conjugate of a complex number. So 1 plus I, and that should get us 1 minus I. Okay. The one thing with complex numbers is we can also form equations, and they are expressed in the form of the left-hand side equals some expression on the right-hand side. Okay, so if we have equation 1 and we set it to 2x plus y equals 5, notice in this example we have, instead of assigning like an expression to a variable, we have now assigned an equation to a variable. Okay, and again, equations, they can be added with other equations, and normally how you solve simultaneous equations, Maple can do the same as well. Okay, so if we copy this code over, so we're adding on 23 equals x, that equation, to our original equation, equation 1, and we're dividing by 3. Unexpected number, equation 1. There we go. And as you can see, we get a nice final equation out. And the last thing is we can use the LHS and RHS to find the left and right hand side of equations. Okay, so RHS of equation 1, that's just simply going to be 5. Okay. One thing that's quite useful with Maple is we can solve for exact solutions. So for example, if we want to use the solve command, this can be used to solve many algebraic equations. So a simple case, if we want to solve 3x plus 4 equals 5, sorry, equals 5x, so 3x plus 4 equals 5x. Normally, if you just have one variable in your equation, Maple knows which variable to solve for. So in this example, we just have x in our equation, and Maple knows just to solve for x. Okay. Whereas if we have more than one variable, so say for example we want to solve the quadratic equation ax squared plus bx plus c equals 0. Notice we have different variables a, b, c, and x. If we just hit enter here, notice Maple just outputs a bunch of gibberish. So essentially here we have to tell Maple which variable to solve for, and in this case we want to solve for x. Okay, solve for x, and as you can see we get the two sides of the quadratic formula. So that's for cases where we have more than one variable. And again, we can assign this into a list. So if we assign our solutions, wrap it around some brackets, that's going to return the solutions inside a list. Okay, and we can do the same operations as before. S of 2 would get out the second element. There we go. Okay. Okay, so exact solutions. Now, again, if we have two equations and like two unknowns, normally you would solve those two equations using simultaneous equations. Maple can also do that for you. So if we have equation 1 and we set it to equal 2 times x plus y equals 5, and we have equation 2 and we set it to x minus y equals 4. Okay. We can tell Maple to solve these two equations simultaneously by again using the solve command. And this time we have to wrap our two equations around braces, so we chuck it inside a set. And we have to tell Maple that we are solving for which variables we're solving for again. We're solving for x and y. Okay, and as you can see, it nicely solves the two equations for us. Okay. And if we again use the assign command, that's going to set the solve variables invalid left side. Okay. Oops. Solving for expressions other than function names. And let me just get rid of this. Okay. What is going on here? In solve. Okay, let's do this again. Solve equation 1 and equation 2, and that should get us these solutions. Solving for other than names of functions. Okay, let me restart here. might be because of we have set different variables. So if you look at the left-hand side, we have a bunch of different variables already assigned. And to just make things clean, I'm going to hit the restart command, and that resets all of the variables. And let's reassign these. So we assign equation 1, assign equation 2, and we solve for it again. Yeah, and there we go, okay? So oftentimes when you run into problems, it probably is because we have too many variables assigned. We just got to hit the restart command and resets everything, okay? And if we want approximate solutions, this is the command fsolve. That's going to be used to find approximate solutions. So if we want to fsolve the quadratic equation, x squared minus 2 times x plus 2 equals 0, and we set x, notice we don't get any solutions out because we have to tell Maple that we want complex solutions, okay? That's going to be involving chucking a third parameter complex, and as you can see, when you hit enter, Maple nicely solves out the equation, okay? And we can also assign it a range of solutions that we want. So say, for example, we want to solve x cubed minus 3x, minus 3x squared, and if we want to plus 2x. And so we're solving for x, and we want solutions ranging from -1 to 3 on 2. That's just going to generate out the solutions in between the range, okay? Yeah, and that concludes the part for complex numbers and solving equations in general. The next part is going to be on plotting, okay? The first part is just simply plotting a single variable. So if we want a function like y equals x squared and we want to plot it on Maple, let's see how we're going to do that. Okay, so let's hit the restart again. The command that we use for plot is just the plot command, okay? And if we want to just graph the generic parabola, y equals x squared, we just chuck in x squared. And the second parameter is the range of x values that you want. Okay, so let's say that x ranges from -1 to 3. And as you can see, we get a nice parabola where the x values range from -1 to 3. Okay. So if we want to plot tan x, so tan x, where x ranges from 0 to 2 pi. We can also specify a third parameter, and that's the list of y values that we want to output. Okay. So if we want y values from -10 to 10. Notice that we get the nice tan graph, and the y values range from -10 to 10, and it gets cut off after. Okay. And the last thing is we can also plot multiple curves on the same graph. And to do that, we first need to chuck all of our equations inside a list. So suppose we have, suppose we set the graphs to be a list of these two equations, and we call the plot command again on graphs, where x ranges from -2 to 4. As you can see, we get the two curves on the same graph using lists. Okay. Now, sometimes equations, they're given to you in parametric form. So that's the case where x is in terms of a third variable t, and y is also in terms of that third variable t. Okay, and we're going to see how we can plot these ones. So normally, the format is we just give it in the given the x function and given the y function, and specify where t ranges from. Okay, so say for example we want to plot the unit circle in Cartesian form. That's again going to be the plot function, and this time we have to chuck all of our parameters inside a list. Okay, and the unit circle is just going to be the cosine t, sine t, and where t ranges from 0 to 2 pi. Okay, and as you can see, we get out a nice, really nice unit circle. Okay, and again, if we've already used our variable t like previously, and we try to do the same thing, we are going to get an error. So if we set t to equal 16, and we try plot the same thing after, as you can see, we get an error, and the error stems from the fact that we've already assigned the t variable previously. Okay, just make sure the variables that you're using, you haven't assigned them to anything before you actually calling the command. Okay. And the last two types of plots that you can get are polar plots and implicit plots. Okay. And these two aren't built into Maple. You actually have to first import the plots package. Okay. And again, remember, to import a package, we use the with command, and inside the with, we have the plots. Okay. And as you can see, we get a list of different extra functions that we can call. And to hide this, we just add a colon in front and hit enter. Yeah. Okay. So the first thing is our polar plots, and that's called by the command polar plot. And inside the parameter the first parameter is going to be our function in terms of theta. Okay. And the second one is where theta ranges from. Okay. So, for example, let's call polar plot of the function r equals 1 minus cos of theta. And theta ranges from 0 to 2 pi. Okay. Hit enter, and as you can see, we get a nice graph depicting our equation r equals 1 minus cos theta. Okay. And as you notice, the background of the curve is also a bit different than what we have previously. This is the polar curve, and they just add in like different arguments and radius just to make things look easier. And the next type of plot is the implicit plot, and that is oftentimes we're given an equation in implicit form. So, for example, the unit circle x squared plus y squared equals 1. To plot that, we would use, again, the implicit plot. Okay. So implicit plot. Let's say we're trying to plot the hyperbola x times y equals 1, where x ranges from minus 1 to 1. Actually, let's do minus 2 to 2, and y ranges from minus 2 to 2. Okay. Hit enter, and this gives us a nice hyperbola. We can also increase the range to make it look clearer. So minus 10 to 10, hit enter, and that would get us a nice looking hyperbola. Okay. Okay. And the last topic is going to be on looking at linear algebra. Okay, so that's everything related with vectors and matrices and all of that. So the first thing is we're going to look at is how to create vectors in Maple. Okay, so let me just restart everything again. Restart. So in Maple we use the less than and greater than sign to define vectors, and all of our elements will be wrapped around these two signs. Okay. And there are two types of vectors that we can define. One's the column vector, and the other is the row vector. The first one is the column vector, and we use a comma to separate out each element, whereas a row vector, we use the vertical bar to separate each element. Okay. So just a quick example, if we want the column vector 1, 2, 3, 4, we just wrap it around these signs, and since we want a column vector, we use commas to separate each element. Okay, hit enter, and as you can see, we get a nice column vector out. Okay. Whereas row vectors, instead of using commas, we used vertical bars. So 1, 2, 3, 4. Hit enter, and we get a nice row vector out. Okay. So two different ways we can define vectors. Now, creating matrices, there are two different ways you can think about creating matrices. First way is you can think about matrices as columns of column vectors, or you can think about them as rows of row vectors. Okay? So notice in the first example here, we have vertical bars separating out each vector. In this case, we have simple column vectors which are separated by vertical bars. So this would depict the case where we have columns of column vectors. Okay. So if we output this out into Maple, let's call this A equals this. As you can see, we get this nice square matrix. Okay. And one thing to notice is that the first element here, this column vector, represents the first column. Okay. The second element, this column vector, represents the second column, and the third vector, 369, represents the third column. And again, we can separate columns using these vertical bars. Okay. So this is the case where we have columns of column vectors. Second way we can define them is through looking at rows of row vectors. Okay. So if we copy the second one over, hit enter, as you can see, we get out the same matrix. But the key difference is instead of these elements are instead row vectors. So the first element here, 1, 2, 3, that represents the first row. Second element, 4, 5, 6, second row, and same with the third element as well. Okay, and remember with rows, these are separated by commas. Okay, and hence we get a row of row vectors. Okay, so two different ways we can define matrices, and there are many functions that come with the linear algebra package. For example, one is going to be linear solve. That's the one that is really useful for you. Okay, so we can import that package again with just calling with linear algebra. Okay, enter. Yeah, and again, you see, look at all of these different functions that we can call on matrices and vectors. And again, if you want to hide this, just chuck a colon in the front and hit enter. Okay, one of the things we can do is extract rows and columns from matrices. That's just simply using the row command and the column command. Okay. So let's define a matrix M. Let it be this square matrix 1, 2, 3, 4. And the first parameter is the matrix that you're calling the row command on, and the second command is the which row that you want to take. Okay, so let's take the first row, and that will get us 1, 3 as we expected. Okay. And the same thing is the same with columns. We can call column M, get the first column, and we get the 1, 2 as we expected as well. Okay. Okay, now, next thing is we can define a series of special matrices. So here we have like 4 main types of special matrices. We have identity matrices, diagonal matrices, matrices of equal elements, and lastly is the zero matrix. Okay. And all of these commands come with the linear algebra package, so you have to make sure that you have imported this package first. Okay. So if we want identity matrix, a 3 by 3 identity matrix, we simply call the identity matrix command and pass in 3 and hit enter, and we get the nice diagonal of 1s. Okay. If we want these diagonal numbers to be different numbers, we call the diagonal matrix command instead and pass in what numbers we want inside. So if we want 1, 2, and 3, notice in this case we get a diagonal matrix with the diagonals 1, 2, and 3. Okay. The next one is we're looking at matrices of equal elements, and that's going to be called by the command matrix. The first two parameters of matrix represents how many rows and columns you want inside your matrix. So if we want a 2 by 4 matrix, first parameter is going to be 2, second parameter is going to be 4, and the third parameter is what we want our element to be. Okay. So if we want our element to be 1, we're essentially creating a matrix of a 2 by 4 matrix with elements 1. Okay. And the last thing is creating the 0 matrix. Okay. That's again called by the 0 matrix command. And if we want a 2 by 4 0 matrix, pass in the parameters and we get a nice 0 matrix out. Okay. Okay. Now, next thing we are going to talk about is Gaussian elimination. You guys might have covered this in lectures, maybe not. But if you do get up to this, solving this by hand is really tedious after you've done like a lot of practice. So Maple really helps out by just doing it for you. Okay. So again, this comes with the linear algebra package. So you first need to define that. Okay. So let's first define the matrix A. And if we want to find the row echelon form of this matrix through Gaussian elimination, we simply can just call the command Gaussian elimination and pass in our matrix, and that would reduce it into the form that you want. Okay. So this essentially eliminates the need to like tedious hand calculations where like you can easily make like a silly mistake. Okay. And if we want to find the reduced row echelon form, we just call the reduced row echelon form and pass in our matrix A, and that most of the times would reduce it into the identity matrix. Okay. Not all the times. And the last thing that we are going to look at is linear solve. Okay. This command is actually really useful. In 1A and Math 1B, you're going to be solving a lot of matrix equations, and solving them by hand would often be like quite tedious. So this linear solve command just solves it for you without having to do any tedious commands. So if you don't know, matrix equations essentially involves this equation AX equals B, where A is a matrix, X and B are vectors, and you want to solve for X. Okay. So again, you would first need to import the linear algebra package. Okay. And suppose we have the matrix A equals this thing over here, and we have the vector B equals this vector here. Okay. And again, suppose we want to solve the matrix equation AX equals B. To do this in Maple, we can simply call the linear solve command. Linear solve. The first parameter is going to be your matrix, and the second parameter is your vector. And hit enter, and that would nicely solve the matrix equation for you and give out your X vector. Okay. Yeah. And that brings us to the end of the workshop. Does anyone have any questions? We'll be free to help around, come around and help you guys out.